Okay, we're at the top of page 22, electrochemistry. Electrochemistry has to do with redox reactions. Understanding a redox reaction is first understanding that this word is a contraction of reduction and oxidation. In a redox reaction, reduction and oxidation occur at the same time. Reduction is when something gains electrons. Reduction is the gain of electrons. And oxidation is when something at the same time loses electrons. Oxidation is the loss of electrons. An easy way to remember that is with this little cartoon character here. Leo the lion says grr. Leo, loss of electrons, oxidation. Grr, gain of electrons, reduction. Now, let's take a look at this reaction up here, which is a net ionic equation. In other words, everything has been removed that doesn't change, just so we can look at the things that are changing. And so we have copper plus 2 going to copper 0, and iron 0 going to iron plus 2. So right away we can tell that this is a redox reaction because we see a change in the oxidation numbers of two things. The plus 2 is going to 0, and the iron 0 is going to iron plus 2. Now this would be the total reaction. And that total reaction can be divided into two halves, two half reactions. One will be the reduction half reaction. Let's write half reactions here. And the other one will be the oxidation half reaction. And each one of them, take a look carefully and you'll see that the electrons are placed on different sides. In the case of the reduction where the copper is gaining electrons, we're going to place the electrons on the same side of the copper. In the case of the iron, which is the species that has lost 2 electrons, we'll place the electrons on the opposite side of the iron. So this is much like when we did kinetics, talking about heat that's absorbed and heat that's released. In this case, though, it's electrons that are gained and electrons that are lost. All right? So what you want to take note of, too, also is, since there are no electrons in the total reaction, you want to see how the oxidation numbers change. So copper plus 2, when it gains electrons, its oxidation number drops down to 0. So in other words, its oxidation number decreases. So as a result of the gain of electrons, oxidation number decreases. And the iron, just the opposite. It's going from 0 to plus 2. Its oxidation number is increasing. So oxidation leads to an increase in oxidation number. All right, now the substance that's undergoing reduction is referred to as an oxidizing agent. It's getting reduced. The reason why it's referred to as an oxidizing agent is because it is causing the other substance or the other thing or species to get oxidized, to lose electrons. And the opposite is true for the substance that undergoes oxidation. It is a reducing agent. So simply put, and I would memorize it this way, I would not change any of the wording here. The oxidizing agent gets reduced, and the reducing agent gets oxidized. If you want, we could note that up here too. Copper plus 2, going from plus 2 to 0, it is getting, in this case here, reduced. Notice how its oxidation number decreases. And the iron is getting oxidized. So note, the species reduced and the species oxidized are always on the same side. They are the reactants. So that's good to keep in mind when they ask you multiple choice questions on this. Now remember, in case you're stuck on where to place the electrons, electrons are placed on the more positive side of the equation. So what I mean by that is, without the electrons, you'd have in the first half reaction here a plus 2 and a 0. The more positive side is the plus 2 side. And the same applies here. You'd have a 0 and a plus 2. The more positive side is the plus 2 side. All right? Leo the lion says grr. One more thing on this panel we ought to know. Let me drop this down. And that is, we're told, redox reactions conserve mass and charge. All right? They conserve mass and charge. And what does that mean? That means they have to balance in terms of atoms and in terms of charges. So if you look at the first reaction, all the way up on top, the total charge on both sides is +2, and the atoms balance. So let's do another one to practice. Now suppose we did this. Suppose we did Na plus Mg plus 2 yields Mg plus Na plus 1. Now the atoms balance in this case, 1 Na and 1 Na, 1 Mg and 1 Mg, but the charges don't balance. Because the total charge on this side, for the Na it's 0, for the Mg is +2. So the total charge on this side is +2, while the total charge on the right side is +1. So there's a charge imbalance. And in order to balance this, we have to change the coefficients, which at the moment are 1, 1, 1, and 1. Remember, the coefficient of 1 is always assumed. So, to increase the amount of charge on the right side, we'd have to multiply this Na by 2. So we'd have 2 times +1, giving you a +2 charge on the right, which counters the +2 charge on the left. But the instant you do that, 2 Nas, you've changed the number of sodium atoms. So you have to put a 2 here. So now the atoms balance and the charges balance. And hence, redox reactions conserve mass and charge. All right, let's do another one for practice. Suppose we had calcium plus aluminum 3. And let's say that produces aluminum 0 and calcium +2. And I'll place the 0 here for emphasis, but typically they don't write the 0 in when it's an element by itself, a free or uncombined element. Okay, so we have a discrepancy, an imbalance here in the charges. Look, +3 and +2. The only way to remedy that, to balance it, is to change the coefficients of the charged particles. And since 3 and 2 go into 6 as their first multiple, you could multiply this by 2 to get a +6, and this by 3 to get a +6. And now, finish it off by balancing the atoms. You now have 3 CAs here. There's only 1 here, so put a 3 here. And there's 2 ALs on the left, and there's only 1 here, so put a 2 here. And so your total charge on both sides, which is +6 in this example, and the total number of atoms, balance. All right, redox reactions conserve mass and charge. We'll practice some of these when we do questions in redox. Again, before I leave this panel, what I suggest is memorizing these definitions exactly as written, word for word. Don't change these words, because these are the words that they use when they ask you questions. Okay? Just memorize it. Place it on a 3x5 card and commit it to memory. All right, let's continue. Now, since redox reactions are all about changes in oxidation numbers as a result of electrons being gained or lost, we have to be able to assign oxidation numbers to different species in these reactions. All right, so there's some ground rules that we should keep in mind in assigning oxidation numbers. First of all, the oxidation number or state, you could refer to it as oxidation state if you like, of a free element, of an uncombined element, is 0. Okay, so let's put in some examples of those. For example, if I just wrote Na by itself with nothing else there, you could assume that is 0. If I wrote H2, hydrogen, with nothing else but hydrogen there, that's 0. Even if I wrote S, let's say 8, again, each sulfur atom there would have an oxidation state of 0, because there's no other element there. Now, secondly, the oxidation number of monatomic ion is equal to its charge. If it's a monatomic ion, we're saying, again, the Na, but in this case, let's put a charge by it, +1. That is the oxidation state, which is the charge of that ion. Monoatomic means a one-atom ion as opposed to polyatomic ions that you'd find in Table E. Okay, let's do another one. Suppose I gave you, as before, Mg plus 2. That would be its charge and its oxidation state. And of course, let's go on the negative side, Cl minus 1. Its charge and its oxidation state. And O negative 2, etc. Next, the sum of the oxidation numbers in a compound is equal to 0. So, for example, if I gave you something like Na plus 1 with Cl minus 1, that adds up to 0. Now, things get a little bit complicated when you start doing compounds that involve more elements other than these simple binary ones. For example, if I gave you something like this, NaClO4. Now, if you're assuming that the Na is plus 1 and the Cl is minus 1, now you're stuck, because what's the oxygen going to be? So there must be a way of working out what each of these elements are, and that is the elements that have more than one oxidation state. And the one that has more than one oxidation state here typically happens to be the Cl. All right? So here are the rules, and I'll show you how to work it out in this specific example. All right? First of all, you assign in order of importance the elements from group 1 plus 1 and group 2 plus 2. They have no choice in the matter. Second, you would assign the elements in group 17, which are the halogens, if you recall. You would assign them a negative 1, let's make that negative a little bit bigger, when they are the most electronegative element in the compound. So you have to keep track of electronegativities in that case, but not really. In most cases, I should say, the halogens will be the most electronegative, because the halogens, if you recall from the periodic table, are the most active nonmetals. All right. And third, hydrogen would be a plus 1 unless this violates the above rules, and I'll explain what that means in a second. And oxygen would be a negative 2 unless this violates one of the above rules. Okay. So, and finally, if the sum of the oxidation numbers in a polyatomic ion is equal to its charge. So if I gave you SO4 negative 2, in this case, you're going to set the total equal to negative 2. Instead of 0, if it were a compound, like let's say Na2SO4. All right, so now let's apply these rules here back to NaClO4. Let me erase here and make some room. I have some of them worked out here at the bottom. But we should go back to the NaClO4 first. Okay, so we have NaClO4. So the first thing I do is I split this up into its elements. And we're going to set the total equal to 0, of course, because, if you recall, this is a compound. It's not an ion where you would see a charge, as in the example here. And then in order of importance, what I'm saying is the first element you assign is sodium with a plus 1, because it has no choice in the matter. And the sodium in this case, since there's only one sodium, would contribute a plus 1 to the total. Next, in order of importance, you would have a halogen where it's the most electronegative here, which in this case, it's not, because the oxygen has an electronegativity which is greater than that of chlorine. Okay, you might want to remember the electronegativities with FOClN, FOClN, fluorine, most electronegative, and oxygen, chlorine, and nitrogen. Okay, so in that order, the oxygen should come next, and the oxygen will be a negative 2. And 4 times negative 2 will give you a negative 8. So if we're looking for a total of 0 here, we're going to need a plus 7 for the chlorine, and since there's only one chlorine, the final answer is plus 7. So what I'm saying is the oxidation number or state of the chlorine in this compound is plus 7, not negative 1, as in the case of NaCl. All right, put a bracket around here to remember the electronegativities. And just remember, Fockel, that's good enough, all right? The fluorine is 4.0, the oxygen is 3.5, this is 3.2, and the nitrogen, I believe, should be 3.0. All right, let's continue. Now, OF2, let's try these. So once again, let's chop it up. OF2, split it. Since it's a compound, we're going to set this equal to 0. And then again, in order of importance, the fluorine is the most electronegative, so we're going to write a -1 here. 2 times -1 is -2. And so we're going to need a +2 here for the oxygen, and there's only one oxygen. So that gives you a +2. Now, if you look up oxygen in your periodic table, you'll see that the oxygen, its most common oxidation state is -2. But using this system, you'll get the rare example here of OF2, where oxygen is +2. All right, let's try this one, sodium carbonate. Na2CO3. Let's split it up. Remember that subscript there belongs to the Na. All right, and we're crashing right here into the C2O4. So let me give that a little more room right underneath it. Na2CO3. Okay, split it up. Again, this is the total on top, and this is the oxidation number underneath it. The first element is a group 1 in order of importance, +1, it's the sodium, but there's 2 sodiums, so that's +2 to the total. The next element in order of importance would be the oxygen. There is no halogen present, so the oxygen would be a -2. 3 times -2 is -6. Looking for a 0 total, since compounds will be neutral. And so the carbon in this case must be a +4, and there's only one carbon, so its final answer is +4. The oxidation numbers we're looking for is +1, +4, and -2. And now here's the fourth guideline that I told you about. The sum of the oxidation numbers in a polyatomic ion. So we're looking at, in this case here, table E, in case you forgot. So C2O4, the sum, as you can tell, it's an ion because of its charge, has to be -2. So what you do is, when you split up the C2O4, what I'm saying is you set the total equal to -2. Now again, oxygen's first with a -2 oxidation state. 4 times -2 is -8. If we get a -2 total, then this has to be a +6, but there's 2 carbons, so that means the oxidation state of each carbon is +3. All right, I have some other examples here broken down for you, just in case you want to do those. And that would be, the oxidation states are highlighted for you. Please don't confuse the total here, the top of the line, with the actual oxidation number. Okay, let's continue now, taking a look at some typical redox reactions that you'll come across. Because redox reactions basically fall into 2 categories, as you'll see. You know what, let's turn to page 2 here. We'll get it. Okay. So looking to the left of your page, I've just enlarged it here so I can elaborate a little bit better on this screen. And that is the types of redox reactions. And the first one is when a metal combines with a nonmetal. Remember, metals are losers and nonmetals are gainers, so we have a loss and a gain of electrons, so therefore it must be a redox. In this case, since the metal is losing electrons, it's getting oxidized, and it would be the reducing agent. So the metal would be oxidized. And if the metal is being oxidized, that must mean the chlorine, the nonmetal, is getting reduced. And certainly it's gaining electrons. And you can tell that from the oxidation numbers. Notice how the sodium increases in oxidation number, and how the chlorine becomes more negative, decreases in oxidation number. So the nonmetal would be the oxidizing agent. All right, let's continue with some more examples. The rest of these examples are your typical single replacement reactions. All right, you might recall from the last unit, I think it was the mathematics unit, we had A plus BC, where A can replace B if A is more active than B as a metal, or if we're talking about nonmetals, if A is more active than B as a nonmetal. In fact, if it's a nonmetal, we'd be replacing the second part of C. All right, and then you get from this, you get AC plus B. So we're talking about single replacement reactions, and to know whether or not one metal is more active than another, or one nonmetal more than another, you'd have to refer to Table J, the activity series. Let's look at this reaction here, referring to Table J, and I'll wait for you to get there. In Table J, so you can see these. You'll see that the magnesium is above the copper. So certainly the magnesium, which is more active than the copper, will replace the copper. All right, and then just underneath this too, you can make it out. In the case of fluorine and chlorine, you'll see that the fluorine certainly will replace the chlorine, since the fluorine is more active than the chlorine. You're looking at the right side of Table J under nonmetals. So the more active, once again, replaces the less active. Okay, and then the third example of a replacement reaction is where you have an active metal replacing hydrogen. You'll notice that in Table J, there are only three metals that are underneath the H2. All right, and that is copper, silver, and gold. So think of it this way, the coins cannot replace the hydrogen. And we mentioned this in the last unit when we spoke about metals that do not react with acids. In fact, this is a metal and an acid. And since the zinc is more active than the hydrogen, is above the hydrogen in Table J, the zinc will replace the hydrogen and free up the hydrogen as a gas. All right. Another point that you ought to note is typically they would ask you, how can you tell if it's a redox reaction, or which of the following is a redox reaction? And in that case, they would have the oxidation numbers, of course, erased. It would just be the raw reaction there. And the question is, how can we tell right away? And the easiest way to do that, I say, is look for free or uncombined element on either side of the equation. So if you look at the equation that we just finished doing, so notice how the zinc is free and uncombined here. How it ends up becoming combined because of this redox reaction. And again, look at the hydrogen, how it's uncombined. So on either side of the equation, where you see free element, then you know it has to be a redox. And let's look at the ones just above this to see how that checks out too. Look at this one here, examples 2 and 3. Free element, free element, free element, free element. So that free or uncombined element on either side of the equation, which ultimately ends up getting combined because of the reaction, indicates that it's a redox. And the same, of course, applies to the very top one. And we have 2 free, uncombined elements getting combined. All right, those are your typical redox reactions. All right, so that's all of page 22. And we can now turn to page 23, if you'd like, where we can talk about the different electrochemical cells. All right, let's take a little break here before we continue.